talking about, obviously, in this course is the notion of integration. And last time I introduced the key definition of what it means for a function to be integrable. Okay, so we are going to be considering a function f on a closed bounded interval ab. And we're going to be looking at the integral of f from a to b. So we require that f is bounded. That's a standing assumption. And we introduce this following key definition that says that the function is integrable if a certain sup equals a certain inf. So what you do is you look at all minorants phi minus for the function. So remember, those are step functions which are less than or equal to f. And we've defined the integral of a step function. It's a pretty obvious thing. A step function just takes only finitely many values. It's constant on these open intervals that are in which how the step function is defined. And so the integral of a step function is just basically the sum of the area of certain rectangles below that graph. Okay, so we have this notion of I phi minus. And what you do is you look at the supremal value of I phi minus over all minorants phi minus. Similarly, you look at all majorants phi plus, and you look at I phi plus, and then you take the infemal value of those. And it's always the case, we proved this last time, it's always the case that the sup is less than or equal to the inf. But exactly when they're equal, that's what it means for the function f to be integrable. And their common value is the integral of f. Okay, so we defined that last time. It's a key definition, and I proved this lemma. So at first sight, I feel like the definition is a natural one, but you can legitimately ask the question, how would I ever check that a function is integrable? And this lemma is really the most common way of doing that. It says that the function f is integrable if and only if a certain statement involving epsilons is true. For every epsilon, there has to be a majorant phi plus and a minorant phi minus for the function, whose integrals differ by less than epsilon. Okay, so I proved that last time, and I put that to good use by computing our first integral. So what I did was I integrated, I showed that the function f of x equals x from 0 to 1 is integrable. And I showed that the integral is 1/2. So let me just remind you how I did that. There's your graph of your function. We picked some integer n, some big integer n, and we looked at this very natural step function below the graph, divided up 0, 1 into n equal sized intervals, and defined the step function adapted to that partition, but it was as big as it could be. And similarly, phi plus is a majorant for f adapted to the same partition. So I computed I phi plus and I phi minus, and I phi minus was a half times by 1 minus 1 upon n, and I phi plus is a half times by 1 plus 1 upon n. So the difference of those two things is 1 upon n. So if someone gave you an epsilon, you just pick n sufficiently large so that 1 upon n was less than epsilon. The difference in those figures then would be less than epsilon. And so we've shown that this function is integrable. Also, the integral necessarily lies between these two values. And it has to lie between this, and that has to be true for every single value of n. And the only possible value that could be is a half. Okay, so that's what we proved last time. Okay, so let's now do a little bit of tidying up. If you remember, I defined I phi for a step function phi. That's its integral, but actually what I'd like to know is that that really is the integral as I've defined it. So we have this little proposition: if you have a step function phi, then it is integrable, and its integral is equal to I phi. Okay, so let's just apply the definition. What we need to do is I need to find, for every epsilon, I need to find a phi minus and a phi plus, whose integrals differ by less than epsilon. That's a very natural choice for phi minus and phi plus. I just take that to be phi. Phi is its own majorant and minorant. So the integrals of those things differ by 0. And so therefore the function is integrable, and the value is I phi. Okay, so that's nice to know. Now, as I said last time, some functions aren't integrable, and here's an example of one. It's the following. It's defined on the closed interval 0, 1, takes the value 1 when x is rational, and takes the value 0 when x is irrational. So sort of schematically it kind of looks like this. There's its graph, all kind of dotty. Okay, so I claim that's not integrable. So what I need to consider is minorants and majorants for it. So consider any partition of this interval 0, 1, x1 up to xn, x0 up to xn. Now, we ask ourselves when we're considering majorant and minorant adapted to that interval, what are the what is the largest possible value of phi minus on the interval, or the smallest possible value of phi plus? Well, any open interval contains both rational and irrational numbers. So therefore, phi minus, because it's strictly below, it's constant on one of these open intervals, and it's less than or equal to f, the largest phi minus can be on any of those open intervals is 0. And the smallest phi plus can be is 1. So that means that any majorant phi plus for f is greater than or equal to 1, except possibly at the finitely many breakpoints of the partition. Those breakpoints don't affect the value of I phi plus, so therefore we show that I phi plus is greater than or equal to 1. Similarly, for any minorant, I phi minus is less than or equal to 0. So the infemal possible value of I phi plus, you can see, is therefore 1, and the supremal possible value of I phi minus is 0. So those two quantities are different, and therefore the function isn't integrable. Just as an aside, if you remember last time I said there are various different notions of integration. We're following Darboux and Riemann integration, and I've just showed that this function f is not integrable in that sense. It turns out there's this more general version of Lebesgue integration, and this function is integrable in the Lebesgue sense. But nevertheless, there are still other functions which are not integrable, even in the Lebesgue sense. Okay, great. So it's just worth knowing that not every function is integrable. So my goal now is to give you various basic theorems about integration. None of these are going to be any surprise to you whatsoever. They're going to be very simple theorems. but actually some of the proofs are going to be a little bit tricky, right? So this sort of foundational work is actually a little bit harder work than you might think. Okay, so remember last time one of the motivations for defining integration, as we have done, is that various theorems become obvious. And one of them is this. This was one that I highlighted last time. Remember, it says that if I have two integrable functions f and g, and that f of x is less than or equal to g of x for every x, then the integral of f is less than or equal to the integral of g. Okay, so let's prove that. The integral of f exists. We're assuming that f is integrable, and it's therefore equal to the supremal possible value of I phi minus over all minorants phi minus for f. Now f is less than or equal to g. So any minorant for f is also a minorant for g. So when we look at the integral of g and we look at the supremal possible value of I phi minus over all minorants for g, well, that includes all minorants for f, and therefore the supremal possible value for g is greater than or equal to the supremal possible value for f. And therefore the integral of g is greater than or equal to the integral of f. Okay, so that's not too bad. Okay, so the next statement we prove is something that you might think almost that you don't need to prove. It looks so obvious, but actually it's not completely so. So what it says is, if I've got some function f that is integrable on the interval ab, and suppose we divide that interval up into two subintervals, AC and CB, then the theorem is that actually it's integrable on each of those subintervals. And, as you'd expect, the integral from A to B is equal to the integral from A to C plus the integral from C to B. Okay, so that's what we're going to prove is exactly what you think is going to be true. Just before I prove it, note that what this means then is that if I have any subinterval, any closed subinterval of the interval AB, call that subinterval CD, if f was integrable on the bigger interval AB, then it's integrable on the smaller interval. You just apply this fact twice. You first of all divide it up and say it's integrable on CB, and then it's integrable on CD. So you just apply that previous proposition twice. Okay, so let's prove this proposition. Okay, so first of all, it's a pretty useful thing. F is integrable, right? So therefore it's bounded, right? That's a standing assumption for integrable functions. So let's say that the modulus of f is less than or equal to capital M. And we're going to be considering partitions of the interval AB. And it's just useful throughout this proof just to assume that any partition includes the breakpoint C. Right? We can always take any of our partitions and refine it without changing the notion of a step function adapted to that. But the step function adapted to the initial partition will still be adapted to a partition if we put C in there, and it won't change the notion of the integral of a step function. So we can assume that all our partitions that we consider include C. And we can also assume that the value of a step function exactly at C is either M or minus M, depending on whether we're considering a majorant or a minorant. And that's just because at a breakpoint, we can set our step function to be any value we want, and that doesn't affect the value of the integral of the step function. Okay, so this is just a little bit of bookkeeping. It's just going to be useful. Okay, so once you've got that set up, then a minorant or a majorant for f, you can think of it as just a minorant or majorant for f restricted to the interval AC, stuck next to a minorant or a majorant for the integral of f restricted to CB. Okay, so minorants for f on the big interval are just the juxtaposition of minorants for f on the two subintervals. And moreover, if we call those minorants on the two subintervals phi minus 1 and phi minus 2, then the integral of phi minus is just the sum of the integrals of phi minus 1 and phi minus 2. Okay, so what we're interested in is we're assuming that f is integrable, right? So we want to look at the supremal possible value of phi minus over all minorants for f. But subject to the above provisos, any minorant for f is just obtained from a minorant for f restricted to AC and a minorant restricted for f restricted to CB. So if we're going to take the supremal possible value of the minorant for f, that's just obtained by taking the supremal possible value of the minorants restricted to AC plus the supremal possible value of f of the minorants restricted to CB. So that means we just get this equality here. Similarly for majorants with infs. Okay, so we're assuming that f is integrable. So just going back to this slide here, what that means is these two quantities on the left are equal. Note that this quantity here, this sup, is definitely greater than or equal to that inf. And this sup here is greater than or equal to this inf. So if I have these two things being the same, that sup greater than or equal to that inf, that sup greater than that equal to that inf, the only way that can happen is if this sup equals this inf and this sup equals that inf. And that's good because that shows that actually f restricted to the interval AC is integrable because that sup equals this inf. And similarly for the second of those two intervals. Okay, so this is just summarizing what I've just said. The sums of those two sups equals the sums of those two infs. The sup involving 1 is less than or equal to the inf involving 1. The sup involving 2 is less than or equal to the inf involving 2. The only way that can happen is if the sups equals the infs, and hence that shows that the function is indeed integrable when restricted to those two subintervals. Okay, good. So that proves that proposition. It was not too bad. Okay, next proposition is that integration is linear. So in other words, if I have two integrable functions f and g, and I form their linear combination in some way, lambda times f plus mu times g, where lambda and mu are real numbers, then the theorem is that linear combination is also integrable, and its integral is just the relevant linear combinations of the integrals of f and g. Okay, so again, something that you're completely used to, but we need to prove this from the definitions. Okay, so actually it's useful to break this down into two simpler propositions. One is that if f is integrable, then so is lambda times f, for lambda a constant. And the integral of lambda times f is just lambda times the integral of f. And statement 2 is that f plus g is integrable with integral equal to the sums of the integrals of f and g. Okay, so it's just to make our lives a little bit easier, we're going to break it down into these two simpler statements. Okay, so let's look at the first of these. So in the first of these, we're just scaling our function f by some constant lambda. So we're assuming that f is integrable. So that means it has a majorant and a minorant whose integrals differ by as small a number as I want. Okay, so someone gives me an epsilon. I need to show that lambda times f also has majorant and minorant whose integrals differ by less than epsilon. Now, the argument is going to break down into three different cases: lambda less than 0, lambda greater than 0, lambda less than 0, and lambda equals 0. So let's do lambda greater than 0 first. So for f, I can find a majorant and a minorant, phi plus and phi minus, whose integrals differ by a smaller positive value as I want. So I can find them that differ by epsilon over lambda. That's good, because now what I can do is I can take those minorants and that minorant and majorant and scale those through by lambda. And because lambda is positive, they stay as a minorant and majorant for now lambda times f. And their integrals just scale by lambda, so the difference of their integrals differ by at most epsilon, less than epsilon. Good, so that shows that, since epsilon was arbitrary, that shows you that lambda times f is indeed integrable. Someone's given me an epsilon and I've found a majorant and a minorant for it whose integrals differ by less than epsilon. Also, that allows us to pin down what the value of the integral of lambda f is. The integral of lambda f is squeezed between the integrals of the majorant and the minorant. So the integral of lambda f is at most the integral of lambda phi plus. That's just lambda times the integral of phi plus. And by the way that we chose phi plus, that's definitely at most lambda times the integral of f plus epsilon. Similarly for minorants, and therefore this integral of lambda times f differs from lambda times the integral of f by at most epsilon. And that has to be true for every epsilon, and therefore the integral of lambda times f has to be exactly lambda times the integral of f. Okay, so we've done case 1 in the case where lambda is strictly positive. When lambda is strictly negative, the argument is similar. Again, we someone gives us an epsilon, and we can find a minorant and majorant for f that differ by a smaller quantity as we want. Let's say they differ by epsilon over, I know how to put the modulus of lambda. So when you scale through by lambda, because I'm now multiplying through by something negative, although phi minus was a minorant for f, lambda times phi minorant now becomes a majorant for lambda times f. The inequalities have flipped because I've multiplied through by a negative number. So lambda phi plus is now a minorant, and lambda phi minus is now a majorant. And their integrals differ by at most epsilon. And so we're done. And then finally, lambda equals 0 is really straightforward. Take any function, take your function f, multiply it through by the constant 0, and what you just get is the function that's identically 0. And that's a step function, right? It's a step function that just takes the constant value 0. And we've proved that step functions are integrable, and their integral in this case is 0. So that's done. Okay, now part 2, which is that the integral of f plus g is equal to the integral of f plus the integral of g. Okay, so someone again gives you an epsilon. We need to find a majorant and a minorant for f plus g, whose integrals differ by at most epsilon. So since f was integrable, I can find a minorant phi minus and a majorant phi plus for f, whose integrals differ by at most epsilon over 2. Similarly, I can do the same thing for g. I can find a minorant psi minus and a majorant psi plus, whose integrals differ by less than epsilon over 2. And then it's clear that if I add those two minorants together, I get a minorant for f plus g. And if I add those two majorants together, I get a majorant for f plus g. And their integrals differ by now less than epsilon. And so therefore I've proved that f plus g is integrable. And just as before, you can work out what that integral of f plus g is by saying that it's within epsilon of the integral of phi plus plus psi plus, and that's within epsilon of the integral of f plus the integral of g. And so therefore, since that was true for every epsilon, and similarly with minorants, you get that the integral of f plus g has to be exactly the sum of the integrals. Okay, so that's the linearity of integration. It's a really useful fact. One other final little bit, I can change my integrable function at finitely many points, and the resulting function stays integrable. And its integral is exactly what the original function was. Okay, so let's prove that. So I've got my initial function f, which is integrable. I've changed it at finitely many points. Let's call this new function f tilde. And then let's just look at the difference between f tilde and f. F tilde minus f is mostly just 0, except at those finitely many points where I change the function. So f tilde minus f is a step function. And it's 0 almost everywhere. And step functions we know are integrable. And this particular step function has integral 0. So f, we're assuming, was integrable. This step function in brackets is integrable. So by what I've just proved, their sum is integrable. And their sum is this new function f tilde. And its integral is just the sums of these two integrals, which was 0 plus the integral of f. So we're done. Okay, so next one in our list of obvious facts is dealing with the maximum and minimum of integrable functions. So the proposition is as follows. You start off with integrable functions f and g, and then you form a new function, the max of f and g. You can also form the minimum of f and g, and you can also form the absolute value of f. or the absolute value of g. And the theorem is that all of these are integrable. Okay, so the first thing to note is that we want to show that various things are integrable, but actually we only really need to focus on one specific thing and show that it's integrable. So there's a series of pretty obvious equalities. The first is that the maximum of f and g is equal to g plus the maximum of f minus g and 0. Okay, so you can see that either by a case-by-case analysis, or by just saying what we're going to do is we're going to take this maximum of f and g and just subtract off g everywhere. When you subtract off g everywhere, you get the max of f minus g and 0. Now just add g back on. Okay? So that first equality, the reason for using that is because that means that I don't have to necessarily consider the maximum of f and g and show that's integrable. If I can just show that the maximum of an integrable function and 0 is integrable, then I'll be done. Because f minus g we know is integrable by what we already proved. Okay, so that allows us to simplify things. It means that one of these functions we can assume is 0. Also, the second inequality allows us, if we can prove something true for maxes, we can prove the corresponding statement for mins. The minimum of h and 0 is minus the max of minus h and 0. And the third thing is that what we're interested in the final part is looking at the absolute value of a function. Well, you can just say that the absolute value of a function h is equal to the maximum of h and 0 minus the minimum of h and 0. So if I can show that the maximum of h and 0 is integrable and the minimum of h and 0 is integrable, then I can show that the absolute value of h is integrable. Okay, so these are all pretty basic equalities, but what it allows us to do is allows us, instead of having to prove lots and lots of different things are integrable, it means that all I really need to do is show that this maximum of f and 0 is integrable. And that's going to make my life a lot easier. Okay, so I've got an integrable function f, and I need to show that the maximum of f and 0 is integrable. Okay, so I could just write down a whole load of inequalities, but what I'm going to try and do is I'm going to try and explain how all of these inequalities that I'm going to be looking at fall into, well, useful pattern. The first thing that I'm going to use is the following fact. If I look at the function that sends a real number x to the maximum of x and 0, then this is order preserving. What that means is that if x is less than or equal to y, then the maximum of x and 0 is less than or equal to the maximum of y and 0. Okay, so this is not very hard to prove. You could do it by case-by-case analysis. But the way I think about this is just by looking at the number line. Here's 0, and x and y are just points on that number line. And when I replace x by the maximum of x and 0, what that does to points is that points to the right of 0 stay put, and points to the left of 0, they just all get sent to 0. So I've taken this number line, I've kept points on the right hand side unchanged, everything on the left has just been shoved up to 0, but clearly the order hasn't changed. Okay, so that explains that. Another useful fact that I'm going to prove is that this function is non-expanding. So what that means is that if I have two real numbers x and y, and I look at on the number line, the distance between them, in other words, the absolute value of x minus y, and then I apply this function to them, in other words, I take the maximum of x and 0 and the maximum of y and 0, and look at the absolute value of their differences, then that's less than or equal to the absolute value of x minus y. And again, if you think about what this function does to the number line, this is pretty obvious. It leaves, when I take an x and I replace it by the maximum of x and 0, when x is on the right-hand side, it doesn't move. When x is on the left-hand side, everything just gets shoved up to 0. But the distances between points have not increased. And so therefore that proves that. Okay, so again, you can prove this by case analysis, but I hope that that explanation convinces you of why these two facts are true. Okay, so we're going to use these two facts in our proof. So it follows that if I have a minorant phi minus for f and a majorant phi plus for f, then when I look at this function max of f and 0, which is the thing I need to show is integrable, then I can create a minorant and a majorant for f for that new function by taking, say, just a majorant for it, by taking the maximum of phi minus and 0 and the maximum of phi plus for 0. Okay, so the way you see that is, well, there are two ways of seeing that. One is by saying what we need to check is that for any given x, when I plug this max of f and 0, x into that function, that it lives between plugging x into that function and x into that function. Well, we knew that phi minus of x is less than or equal to f of x is less than or equal to phi plus of x. So we have that order. Now take max of everything with 0. We've seen that that is order preserving, and so therefore we get these inequalities. Okay, so that's one way of seeing it. Another way of seeing this is that what we're doing here is we've got my function f, and I've got some minorant and some majorant for it. Let's say I've got some minorant. And then what I do is when I take the maximum of f and 0, I get this function. F is unchanged when it has positive values, and it just hits 0 here. And what do I do to the minorant here? Well, when it has positive values, these are unchanged. But when it has negative values, they become 0. Okay, but it's clear that that's still a minorant now for the max of f and 0. Similarly for majorants. Okay, so from a minorant and majorant for f, I've created a minorant and a majorant for max of f and 0. And I mean, I could have just taken phi minus. That still would have been a minorant for this function. But it wouldn't have been as an efficient minorant as I need. I want to try to show that the minorants max of phi minus and 0 and a majorant max of phi plus of 0 are efficient in that their integrals differ by a small quantity if the integrals of phi minus and phi plus differed by a small quantity. Okay, so what I really need is that the difference of the integrals of this new majorant and this new minorant are at most the difference of the integrals of phi plus and phi minus. And what we'll see, I mean, you might be able to just see that, but really what we're going to be using is the non-expanding nature of this function, max of x and 0. Okay, so let me just put a little bit of flesh on this by kind of writing down a full proof of this. Okay, so say that we may as well assume that phi minus and phi plus are adapted to the same partition, say a equals x naught less than or equal to x1, etc., xn equals b. And say that phi minus takes the value c minus I on the interval, actually let's put it here, ci minus on the interval xi minus 1 xi. Okay, so it's constant on that interval, and say it takes that constant value. And say also that phi plus takes the value ci plus on that interval. Okay, so what I want to do is I want to look at the difference of these two integrals. Okay, so we're interested in the integral of the max of phi plus and 0 minus the integral of the max of phi minus and 0. And I want to find an upper bound on that. I want to show that it's the most integral of phi plus minus the integral of phi minus. Okay, so let's plug in the formula for the integral of a step function. This is the sum from I equals 1 to n of the width of the relevant interval times by the value that that step function takes on that open interval. So this is equal to the maximum of ci plus and 0 on that interval, minus another sum, but now for phi minus. Okay, so I can clearly take those two sums and amalgamate them into a single sum. Like so. And here in this term is I have the maximum of ci plus and 0 with 0 minus the maximum of ci minus and 0. And so by the non-expanding inequality, the non-expanding nature of that function, that is therefore less than or equal to ci plus minus ci minus. But here, this is clearly equal now to the integral of phi plus minus the integral of phi minus. And we're done. Okay? So that's just putting a little bit of flesh onto why this is true. Great. Well, we're now done because given any epsilon, I can find a phi plus and a phi minus whose integrals differ by less than epsilon. Now I found a majorant and minorant for the maximum of f and 0, whose integrals therefore also differ by less than epsilon. And therefore I've shown that this maximum of f and 0 is indeed integrable. And that's what I needed to show. Okay, so I basically covered the sort of elementary results that I want to cover in this lecture. No great surprises here. Linearity of the integral, the fact that if a function f is integrable, then max of f and 0 is integrable, that the absolute value of f is integrable, etc. These are all completely predictable, but they're still interestingly tricky, and we're not quite yet done. We're going to do one more tricky thing next time, which is that if f is integrable and g is integrable, then their product is integrable. But that's going to be a little bit harder than any of these proofs. But again, totally not surprising. But once we've done that, we will have a whole basket of functions which will be integrable, right? So we know that the function f of x equals is integrable. Once we know that the product of two functions is integrable, that'll give us the x squared, x cubed, etc. integrable. We know that the sum of integrable functions is integrable, and similarly if I scale functions by a constant, they're integrable. So that will then show us that every polynomial is integrable, which is a good start. Okay, so that's all next time. Thanks very much.